Okay, around 30 students have joined so far. You can mark your attendance. Within 1 minute, we shall start with the lecture. Attendance is already enabled. Okay, hope all of you uh, have marked your attendance. Uh, so we have already started with the unit 5, that is memory organization, memory and IO organization. And in that, in the last class, we have already discussed about the characteristics of memory. Now, the next point to be discussed in the memory organization, which is one of the important uh, point in the memory, is in the memory organization. It is the cache. Okay. So cache is the high speed memory which is present between the central processing unit and the main memory. Okay. I hope I am audible to all of you clearly, loud and clear. Somewhere some microphone is unmuted. Mute it and concentrate on the slides which I am presenting. Hope the slide is visible to all of you. So cache is the fast memory. You have been listening about the cache whenever you are buying laptops or desktops. So in that case, we talk of how much cache that particular device has. So if the device has cache, then that device is said to be or will be functioning faster than those devices who do not have cache. Okay, or uh, the more amount of cache will enhance probably the uh, speed of execution of that particular device. But always that is not true. To certain extent, if you increase cache, then it will improve the performance, but after that it may not improve that particular performance. So unnecessarily we should not spend a lot much on the cache, but still we should be aware that how much minimum cache is required so that the required speed of operation is there. Okay, so we shall study the organization of the cache and how the cache functions and how CPU operates with this particular cache. So we discussed that the cache can be either a single cache or it can be organized as the different levels of the cache. That is, in the cache also you have some memory which is fastest, some memory which is less faster, and some memory which is slow. Okay, but though it is slow, but it is not slower than the main memory. The main memory is the slowest one in the internal memory. So this particular cache memory can be organized in the different levels even. Okay. Now let us see the different basics related to the cache memory, the performance metrics of the cache memory, and how to improve the performance of the cache memory. So the structure of the cache memory or the main memory is something like this. So main memory is a huge memory. Okay. Usually this main memory is implemented using dynamic RAM. Okay, so popularly it is called DRAM, and this memory is slower. If CPU directly reads or write from this main memory, then the time required for fetching the instructions, the time required for reading the data or writing the data in the main memory. So this the memory access is more if CPU is directly reading or writing from the main memory. Okay. But if CPU is reading from some memory which is faster, for example, the static RAM is faster, and CPU can read or write or fetch instructions from the memory called the cache memory. In that case, the time required for fetching the instructions or for reading the data or writing the data into the memory, it will be drastically improved. So CPU have this static RAM, then CPU will directly read from this particular static RAM. So this is the implement of the main memory using the static RAM. But there are other parameters like first one is the cost. Okay, that is the cost of the static RAM is more. Even if it is more, let us say if somebody is ready to pay that more cost, but the size, that is per bit size for the dynamic RAM, it is very less. So it is possible to accommodate many bits in a smaller size, whereas for the dynamic RAM, the size is large. Okay, typically, if you want to compare the size required for the dynamic and static RAM, the static RAM for its implementation, that is to store one bit, you know that the static implementation can be done using the flip-flops. So for that implementation, you need, even if you go for a very compact implementation, you need almost six transistors. Okay, you need six transistors. Okay, you need number of gates to build a flip-flop. Total six transistors are required to build the to build a particular 1 bit storage, okay, in static RAM, whereas that can be done with just one transistor in the dynamic RAM. Okay, so the size is larger for the static memory, whereas one more another point, that is the power requirement for the static RAM is more than the dynamic RAM, because it is uses more number of transistors, so naturally that will be higher. So the power requirement is higher. Now if power requirement is higher, that means if it is consuming power, then it has to dissipate the power also. That is, whatever power is consumed, it is dissipated by the transistor in the form of heat. So this particular static RAM, the heating problems are there, and so you need to provide the cooling system, and if you do not have the proper cooling system, then in that case, what may happen is that it may burn your circuits. Uh, so that is why the dynamic RAM are used in huge size. Okay, but the small amount of the static RAM in the form of cache can be there on the board. Okay, so that is how uh, you can work with the or you can have the static RAM in your system. So that is why you need to have a static RAM. Okay, or so advantage is that it is faster. So a combination of the dynamic RAM and static RAM, that is main memory implemented in dynamic RAM, and the small amount of memory implemented as cache. So that is the best combination found, and that is being used uh, in the many devices, that is in the computers, for storing the information. Okay. So what is done is that the main memory is divided into a number of blocks. Okay, so we can see here that this particular memory is divided into blocks, and this is block number 0, then followed by that it will be block number 1, 2, 3, 4. So there can be as many as, let us say, m number of blocks in this particular main memory. So a particular block may consist of k words, k number of words. Okay. So the main memory is divided into number of blocks. Then your cache is also divided into the number of blocks, and size of each block is k word. That means the size of the block in the cache memory and the size of the block in the main memory, it is same. Okay. So it is possible to select any of the block from the main memory, and you can transfer it or you can copy it into any one of the block location in the cache memory. Okay, so in the cache memory, the number of block locations, so those are called lines. The block locations in the cache memory, they are called the lines, and these lines are given the numbers, that is 0, 1, 2, up to c minus 1. That is, each line it contains k number of words. Okay, so you can copy any of the block and you can put it into any of the line, that is the block location, because the number of words that can be accommodated in each of the line, it is the k number of words, that is number of words in one block. Okay. The point to be noted here is that there are m number of blocks in the main memory, whereas there are c number of lines in the cache memory, you can say, or simply cache. So the number c, that is the number of lines in the cache memory, they are usually very much smaller. They are very much smaller than the number of presents, the number of blocks that are present in the main memory, that is m. The number m is much larger than the number c. Okay. So what is done is that some of the blocks which are currently required by the CPU, okay, some of the blocks from the internal uh, memory, that is the main memory, some of the blocks from the main memory which are currently being required by the CPU, they are kept in this particular cache memory. So how many blocks can be kept in the cache memory? So that depends on how many number of lines are there. So there are c number of lines. So CPU can work with c number of blocks from this main memory. All these blocks, they are transferred to this particular uh, cache memory. Okay. Now the thing is that when you are transferring a block, so this particular transfer is memory to memory transfer. So when you are moving a block, that is k number of words, from the main memory to the another memory, that is the cache memory, then this particular transfer, that is memory to memory transfer, if we use some architecture, specialized architecture for doing this, or we make the architecture of the processor such that it is possible to transfer these particular blocks from main memory to this particular memory with higher speed. So this is called the memory to memory transfer, and usually this is done by a specialized hardware, and that is called the DMA controller, that is direct memory access controller. We shall not go into the details of that right now. In the IO organization, we shall see the DMA controller. Okay, but for your information, because somebody may raise the question that time will be spent in transferring the block from main memory to the cache memory, and then the CPU will be reading from the cache memory. Okay, but though the time is required for transferring, but because it is the memory to memory transfer, it is done with specialized hardware which require when a particular block is being transferred. Okay, so the selected blocks, they are copied into this particular cache, and then it will be possible for the CPU to read directly from this particular cache. Okay, when CPU find that some block is not present in the cache, then in that case one of the blocks, one of these C blocks which is not required by the CPU, it will be replaced with the newly required block from the main memory. So from the main memory, that particular block has to be transferred here. Okay, so this can be explained, the cache read operation can be explained with this particular flow chart. So the CPU starts with its read operation here. So it receives the address, that is it first, usually that particular address is there in the instruction pointer or uh, uh, the program counter. Okay, so it reads the instruction address. Okay, then it it checks if the block is contained Hello students, there was interruption. Hope I am audible now. There was an interruption in my connection. Hope I am audible now. Somebody respond if I am audible.
Yes, sir, audible.
Okay, so uh, so continuing with this, whether this presentation is visible to you?
No, sir. Currently, nothing is visible on the screen.
Just a minute. Visible now?
Yes, sir.
Okay. So continuing with this. So after the CPU first checks if the read address is there in the cache. That means whatever CPU wants to read, if the read address is the part of any of the block, if it is yes, that means that particular block is present in the cache. Then what CPU does is that it fetches the read address uh, word from the cache. Then it is done with that particular read operation. Okay, but if the read address is not present in the cache, then what it does, it accesses the main memory for the block that which contains that particular read address. Then it allocate a line for the main memory block. Okay, so a line will be allocated. So for allocating the line, it may be looking for a free line, but many times the free line may not exist. So in that case, some line will be swapped, that is some line from the cache will be removed, and this particular new block will be put into or it will be loaded into that particular cache memory. Okay, so the new block will be loaded in the cache, and simultaneously what happens, the uh, the uh, the word to be read from uh, the word to be read from that particular block will be read by the CPU, and then CPU is done with that particular operation. That means when some word is not found in the cache, then the whole block is transferred from the cache to uh, the whole block is transferred from the main memory to the cache. Okay, so when one word is not found, then in that case, when CPU go for the subsequent read operation, then it is likely that the next word will be from the same block, and because already that particular block is fetched in the cache, so next time it did not have to go through this particular path, and it will directly read it from the cache. Okay, so most of the time CPU will be finding that whatever it wants to read, it is present in the cache memory. That is, out of let us say 100 read operations, 98 times CPU finds that whatever it needs to read, it is present in the cache, while only 2 times out of 100 this particular block transfer is required. So you can say that with the cache is to be designed in such a way that the hit rate. Okay, so hit rate, what is hit rate? Hit rate is the rate that is the percentage as to how much time that a particular word is found in the cache. Okay, so if you design the cache such that the hit rate is 100%, then in that case this particular operation of the CPU will be much faster than without the cache. Okay, so this is typical cache organization which we already discussed. The system bus, and this particular cache is connected to the system bus, and whenever block is to be transferred, it will be transferred from the system bus into the cache, and once it is there in the cache, then processor will be directly reading from this particular cache, okay, without going to the main memory. Okay, So there are various elements of the cache which are important when we talk of the performance of the cache memory. So let us see the important cache elements which are important in designing the cache. So the first of all, the cache is related with the addressing, what addresses it uses. So whether it uses the logical address or the physical address. Okay. So usually in the instructions, whatever address used is the logical address, whereas the main memory it uses the physical address. But as far as the cache is concerned, it uses the logical address. It uses typically memory called the CAM, that is content addressable memory. So with which it is usually uh, uh, easier to locate quickly whether a particular uh, address is present in the memory or not. If it is present, then immediately that particular contents are read. Okay, so a kind of logical address is being used in the cache. So this particular logical address also uh, it also helps in implementing the virtual memory. So we shall see what is that particular virtual memory. Okay. What is the cache size? That also matters. So if you are having very small amount of cache, then that may not improve much the performance, the speed of execution. So if you go on increasing the cache memory with a particular device, then its performance or speed of operation will increase. But increasing the cache size above certain limit will not improve the performance much. So there is you can say balance between the performance and the speed and the size of the cache. So we need to balance it properly. Okay, that is, we should not have very large amount of cache, because that will not really increase the performance, but definitely it will increase the cost of the system. It will increase the power dissipation in the system and like that. Okay. What is the memory or what is the mapping function that is used? That is, whenever a block is transferred from the main memory to the cache memory, so which particular block, or how blocks from the cache memory, the main memory, are are mapped with the cache memory. So there are three different types of mapping functions: direct, associative, and set associative. So use of proper mapping function will also uh, decide the performance. Okay, we shall see this particular mapping functions. Then in the case if a particular uh, block is to be brought into the cache, but there is no space left in the cache. All lines in the cache, they are occupied. So in that case, you need to go for replacing some block in the cache. So which particular block is to be replaced? So because that it may happen that you are using your it may happen that you are replacing some block which may be immediately required by the CPU, and if you are replacing that particular block, then that will be the bad choice for the replacement. Okay, while the best choice will be the block that is never required by CPU after that. Okay, so that that particular block can be replaced. So various algorithms are there which will select the block to be replaced from the cache, that is least recently used, that is LRU, or first in first out, that is FIFO, that is LFU, that is least frequently used, and random, that is you can randomly select the block. So sometimes it is found that even if it is randomly selected, but the performance, that is the performance with this particular random is comparable with the other schemes. Okay, why? Because the other scheme, they require a certain algorithm to be implemented in the hardware, and the cost of implementing it, those particular algorithms, they are complex algorithm. uh, so that is why the implementation cost is higher, whereas the implementation cost for the random algorithm is lower. Then what is the right policy for the cache? So that is also important, and that also decides or determines the performance of the cache. That is the write through policy or the write back policy. Two different write policies are there. What is the size of the line? Okay, that is what is the size of each block, that also matters. Okay, and the number of caches, that is whether there is a single cache or two levels of cache, or that is the multiple levels of the cache. So that also matters, or that also decides the performance of the cache memory. Nowadays it is very common to have multiple level of cache, like in the recent processors like Pentium processor, usually there are three levels of cache. Okay, so you can see this particular diagram uh, in which various processors and the computers are being shown here. Uh, this particular in these particular systems, the how much cache is used, and what is the level of cache is being shown here. Of course, this table is a little old. It is from the book of Stallings, maybe 8 to 10 year before, but you can get the idea of the use of the cache by the devices. Earlier, only one cache was used, and the size of the cache, it was in kilobytes. So that was the case in 1968. Okay, so even with the uh, uh, before the micro processors came, the it was the this particular type of cache was being used, though it was not common in all the machines. But from the Pentium processors and the PCs came, the use of the cache memory was common. Uh, so, but it was in kilobytes only. But nowadays you can see that the cache, it is in gigabytes, though the L1 cache, it may be in still in megabytes, but the L2 cache and the L3 cache, it is in megabytes or gigabytes. So for this particular server, this is in 2011. So this is the cache being used there as a L1 cache, 128 kilobytes. L2 cache, 24 into 1.5 megabytes, or the L3 and L4 cache, that is 24 megabytes and 192 megabytes. Okay, but nowadays you'll find that it is in gigabytes. Okay, so various processors have been shown here that are using the cache memory. So it is very common that the processors use the cache memory. Now, one of the very important you can say uh, feature of the cache is the mapping function. Okay, so how the uh, the block from the main memory is mapped with the cache memory, which mapping function is used, because this particular mapping function, if it is not properly used, if the correct mapping function is not used, then that may degrade the performance of that particular system. Okay, so as I told that three different mapping functions are there. So on the third mapping function is the most useful, or you can say the efficient mapping function. But in that case, you need to properly set the sizes of the cache and and the number of lines in a particular cache. So suitable cache size you should select, so that the performance of that particular system will be as per the expectations. Okay, so the first mapping function, which is the simplest technique, is the direct mapping function. So it maps the each block of main memory into only one possible cache line. Okay, so there are a number of cache lines, and where that particular cache line is to be mapped, it is fixed. So this particular mapping is expressed as I is equal to j modulo m. Okay, so that is j mod m. So I is the line number that you get, and what is j? J is the uh, main memory block number. Okay, so there are a number of blocks in the main memory. So where to transfer this particular jth block? Okay, so if the jth block is to be transferred into the cache, then where it is to be transferred into the cache memory is decided by this particular formula, that is j I is equal to j modulo m, or j mod m. That is, what is m? M is the number of lines in the cache. Okay, so let us say, for example, if there are total 100 there are, let us say, 100 uh, uh, you can say blocks in the main memory, and there are only 10 lines in the cache memory. Okay, so the cache memory will be given the line numbers, that is 0, 1, 2, 3, 4, 5, 6, 7 up to 8 and 9. Okay, whereas uh, the block numbers in the main memory, because there are 100, so they will be given the numbers, let us say, from 0, it will be 0, 1, 2, 3 up to 99. So let us say the block number 54 from main memory is to be transferred to the cache. Then what is the formula used here? That is j modulo m. So 54 mod m. So 54 mod 10. So what is that? 54 mod 10. It is mod means the remainder the remainder operator. Okay, so
4.
54 mod 54 mod m.
Sir,
It
4.
is yeah 4. So the it will be transferred into the cache at the line number 4. Okay, if it is 67, if the main memory block is 67, then using that particular formula, that is 67 mod 10, so that will give you how much is
7.
that? 7. Okay, that means at line number 7 it will be transferred. Okay, now because the numbers, they are from 0 to 99. Okay, and because the you are dividing it, okay, that number m is 10. So whatever the result of is there, the remainder, because you are dividing by 10 and you are taking remainder, so the remainder will be always less than 9. So you will get 0 to 9. Your remainder will be always 0 to 9. So it is fixed, that is which particular block will be moved. That means whenever block number 67 is to be transferred, it will be always transferred to line number 7. Okay, so you can see here that if there are if m number of blocks are there, so here the block number m number of lines are there. So block number 0, block number m, block number 2m, up to 2 to the power s in minus m. So this particular block, if they are to be transferred in the cache, they will be transferred to line number 0. Okay, so in our case, that is block number 0, block number 10, block number 20, block number 30, block number 40, 50, 60, 70, 80, 90. So this particular block, if they are to be transferred into the cache, then they will be always transferred to line number 0. Okay, for example, the at line number 1, which block will be transferred? That is, if main memory block 1 or main memory block 11, 21, then 31, 41, 51, 61, that is up to 91. So if they are to be transferred, they will be transferred to this particular line number 1. Okay, that means we can say that this cache line, this particular cache line 0 is shared by the main memory blocks, that is block number 0, 10, 20, 30, 40, 50, 60, 70, 80 and 90. Okay, so that is 10 blocks they share this particular cache line. That means one of these 10 blocks can be there in this particular cache line. Okay, so in the similar way, one of the 10 other blocks, that is 11, 1, 11, 21, 31, 41 up to 91. So one of these 10 blocks, they can be there in the cache, that is at cache line number 1. So this particular block, they cannot be transferred anywhere but at this particular line. So this type of mapping, it is called the direct mapping. Okay, so this is the diagram explaining this particular direct mapping and how this particular direct mapping takes place, or how this particular CPU does this particular direct mapping. Okay, so quickly we shall see this, or I think it will take little time to explain this particular diagram in detail as to how this particular memory address is being used and what is this tag and all this. Uh, we shall defer the explanation of this particular direct memory cache organization till the next class. Okay, because it is time to for you to join the next class. So today we shall stop here. If you have any quick doubts on whatever we have discussed about the organization of the cache and the features of the cache, we shall I shall answer it quickly if required. Okay, so have you understood what we discussed today? If not understood, some part can be again taken in the next class. I hope you have understood this, and we shall continue with this cache organization in the next class. I hope all of you have marked your attendance. Those who have not marked, you can stay back. I will quickly mark it instead of sending the message. Others may leave now and join the next class. Everyone marked attendance? Anyone left?
Hello, sir.
Yes, Shreyas.
Sir, roll number 72.
You could not mark your attendance.
Yes, sir.
Just a minute. 72, Shreyash.
Shreyash nahi, sir. Rohit.
Okay. Serial number and roll numbers are different here. Rohit, no?
Yes, sir.
Okay, marked.
Thank you.
Hello, Sakshi, leave the meeting.